these elements, iron, zinc, and thallium. I think we've actually done all these elements in the past in terms of predicting their ions, and that's okay. But what we're going to do is we're going to break up into groups. Now, I've noticed that when we break up into groups, it's possible for the person who's the group presenter to actually allow everybody to write on the surface. I haven't figured out how to kind of clear the slide up yet in the breakout group, so you're kind of writing on top of what's already there. But if whoever's in charge then gives everybody the opportunity to help write the the electron configuration for these, and then predict ions, right, in your little breakout groups, I think that would be effective. So again, we're going to try to predict the kinds of ions that these elements will form, and this is kind of a review because we have done these before, I think, but you might learn some stuff as well. So let's go into our breakout rooms here, and let's see here. We'll do 3 different rooms. There we go. All right, so go ahead and join these rooms, and we'll see what we get.
Maybe.
Yes.
Okay. So,
All right.
15 iron. Ions.
So, do you guys want to write the electron configuration for zinc? Maybe Samantha, you could write the electron configuration for zinc. I'll write the electron configuration for iron here. So if you choose a pen tool off to the right there. Whoops, uh-oh, it's going to be ugly. The electron configuration for iron. And then James, you want to write the electron configuration for thallium down below there?
Sure.
Let's see. Noble gas electron configuration, right? So argon for iron. All right, Taiwan, what do you think? Looking at my beautiful electron configuration of argon there, I have 4s2 3d6. What do you think, Taiwan? What would a reasonable ion be that iron would form based on this electron configuration? What kind of an ion would we expect? Taiwan? That's right, +2. Very good. A +2 ion. Because why? What electrons would we be losing, Taiwan? Why don't you circle the electrons we'd be losing? That's right, we'd be losing those 4s2 electrons. Very good. Now, after those 4s2 electrons are gone, and we have our +2 ion, right? What, if any, additional charged species might we expect? All right, what are we going to do with those 3d6s? Or 6 3ds? plus 4. All right, so let's draw these 3D. 1, 2, 3, 4, 5. This is our 3D, right? Fill it up for us, Taewon. How many do we have? 1, 2. I'll help you out here. Well, the Fe2 plus. What does the Fe2 plus look like? 1, 2. We have, and before we took any more electrons away, we had argon 3D 6. So we have 6 electrons. 1, 2, right? So 3, 4, 5, and then we need one more. I want to put one more in there, Taewon. 6. Very good. So we had 6 electrons. And now if we form a plus 4 charge, it would be removing 2 electrons from here, right? And that, to remove 2 electrons from here, would actually probably not stabilize it much, because the first electron, to remove 1, it would leave us a half-filled subshell, which is nice. But if we remove another one and make a plus 4, I think we would destabilize it. So it's likely that we'll lose this 1 electron here, but that's it. If we only lost 1 electron, Taewon, instead of a plus 4, what would it be? Plus 3, right. Very good. So let's look at Samantha's zinc. What do you think, Samantha? What kind of a charged ion would zinc form?
+2.
A plus 2, that's right. By losing which electrons? That's right, the 4s2 electrons. Very good. Now, can you think of another ion that zinc might want to form? What do you think, Samantha? Any other ions that zinc might want to form?
+1.
All right, that's a guess there, right? We knew that we would like to get rid of those high energy, the 4 electrons, but maybe you recognize that after we have our 4s2 gone, then this 3d10 would look like this, right? Completely filled. And to lose an electron from there would not stabilize our situation. And so that's actually why zinc only forms a +2 ion, right? Because we can lose these electrons, but then after we were left with the 3d10, it's not going to improve things to lose any more electrons. All right, so James, tell us the 2 ions, and that's a hint. What are the 2 ions that thallium would like to form?
+3 and maybe +2.
Okay, what about a +1? Can you see why it might want to form a +1?
Oh, just lose the 6p1.
That's right.
Okay.
Very good. So we got thallium forming a +3, or possibly just losing, whoops, that's supposed to be a 1. Possibly just losing the, oh, look, I can erase that. I wonder if I can erase all this. Nice. Huh. Well, yeah. If we just lose our 1 3p electron, then we'll form a +1 ion there. Or 6p1 electron. All right, very good, gentle people. Let's close our breakout rooms, and we'll all go back together. All right. Are we all here? Anybody want to talk about what they learned? What kind of ions can we predict about iron? Harry, you want to tell us?
So our group got either a +2 or +3 charge.
All right. Very good. So what's lost to form a +2 charge here, Harry?
The 4s2.
The 4s2. Very good. And then why did you say that it was likely that a +3 charge would also form, looking at this electron configuration?
Because if you take away one more electron from this 3D subshell, all 5 are going to be half-filled.
That's right. So 5 orbitals in a 3D subshell. If we had 6 electrons, we're really close to having just a perfectly half-filled subshell. So removing one would increase the stability slightly. Very good. Okay, James Oliver, how about zinc? Did you get to talk about zinc, James Oliver?
Our group decided it was just +2.
Okay. And why did you decide that nothing else could be lost beyond that 4s2? What's our rationale for that?
Because the D subshell was already filled, so taking away like an electron would just make it stable.
Okay. Very good. James, tell us about thallium. James Willis.
Thallium would form a +1 or a +3 ion.
All right.
+1 losing the 6p1 and the +3 losing the 6p1 and the 6s2.
Excellent. Very good. So the 6p1 will separate from the 6s2 sometimes, because the 6p1 is actually higher in energy than the 6s2, right? So the highest n values are the electrons that will go first generally. And if you have 2 sets of electrons with the same n value, then the L value, and what is the L value that corresponds to S, James? Do you remember?
For S, L equals 0.
Very good.
Right?
Yep, that's right. And so for P, L equals 1, and that is our secondary quantum number, which does tell us a little bit about energy. All right, very good. So that's our method for predicting ions. Here's one more of the charges that are provided here. Which one would be a likely charge for the antimony ion? Why don't you guys all take a look at this? 18 seconds, get an answer, and then we'll talk about it. And let me bring up a periodic table here, just in case you're wondering where antimony is. Number 51 here. Which one of these is a likely charge for antimony? Okay, Catherine, what do you think?
+3.
+3, that's right. Antimony would like to lose these. What is this shell where antimony would be losing its electrons, Catherine? What's this subshell here?
4p.
4p, that's right. It would like to be losing its 1, 2, 3, 4. Actually, that's 5p, isn't it? 1, 2, 3, 4, 5p, yeah. It would like to lose its 5p's. And then after it lost its 5p's, what do you think, Katie? Which would it likely lose next?
5s.
That's right, the 5s over here. All right, very good. So, I think we got it. We'll move ahead to a few other things. We'll look at this briefly, showing that these electron configurations can also be used to predict ions for nonmetals, all right, anions, right? Now this is less than exciting because our old method for predicting ions for anions was to look over here at the nonmetals and just count how many electrons were necessary so that it attained a noble gas electron configuration, right? And that's because that's so easy, it would seem a shame to write the electron configuration for oxygen and then try to use this to figure out what a stable ion would be for oxygen. But you can see that you could do that, right? You could look at your 2p4, imagine that in your mind, right? 2p, 1, 2, 3, 4, and then say this oxygen atom wants to have 2 more electrons, right? Okay. Now, we're going to introduce to you something, a concept, a tool that is used to talk about bonding of not ionic compounds. So a lot of what we've just talked about is bonding about ionic compounds. But now we're talking about bonding for, I mean, when ionic compounds form bonds, it's because they've lost electrons, created ions, right? And those ions are attracted to whatever species they gave their electrons to, right? And so understanding electron configurations tells us about helps us predict ions. And so that's why it's about bonds, bonding in ionic conditions. But we haven't really talked about bonding under molecular conditions. So a different tool is better for us to talk about bonding for molecular conditions. And that is called, the tool is called Lewis structures, understanding Lewis structures. Now, Lewis structures, kind of like the noble gas electron configuration of elements, only deal with the valence electrons that are on a given element. And the way we kind of write Lewis structures is we write an element of interest. So, for example, let's think about bromine, for example, to start off with. Bromine. If I want to put the number, or write its Lewis structure, what I do is I identify its number of valence electrons, right? Now, you could do valence electrons using your electron configuration, that's fine, but I think that for nonmetals, and again, Lewis structures are valuable for nonmetals, it's pretty easy to use the periodic table to count up the number of valence electrons, right? Essentially, we can look at the column here. This is the 8th column. If we start here, 1, 2, skip all these, 3, 4, 5, 6, 7, 8. If we just count our representative elements, those 8 like that, then that column indicates the number of valence electrons that are on that atom. Okay, so bromine is in our 7th column, and you know, generally, again, talking about valence electrons for these elements is only helpful when you're wondering how many are the kind of ions they're going to form. So we won't be drawing Lewis structures of these very much, but Lewis structures will really be helpful in describing and understanding molecular compounds. Okay. So bromine, let's see if Landon can tell us how many valence electrons does an atom of bromine have. How many valence electrons?
According to what we just talked to Sarah late.
Oh, that's fine.
Is it 7?
It is 7. It's 7 valence electrons. Now, Landon might have just come in, and so he didn't catch how easy that was. We could have done our electron configuration for bromine, right? Argon, 4s2, 3d10, 4p3, 4p6. Wait. 4p5, sorry, 4p5. Electron configuration for bromine there. And then we can count up, right? 2 plus the 5, that's our 7 valence electrons. But what's an easier way to do it, Nikki?
Can you just see that it's in the 7th row or column?
That's right. That's right. Just see that it's in the 1, 2, 3, 4, 5, 6, 7th column. And so it tells us how many valence electrons there are. Now don't forget, just because we've identified that bromine has 7 valence electrons, it doesn't mean that's all the electrons that bromine has, right? So when you write the number of valence electrons for something, sulfur, for example, how many valence electrons does sulfur have? Precious?
Six.
6, that's right. It doesn't mean it only has 6 electrons. It has 6 valence electrons. Total of 16 electrons, still based on the atomic number there, right? So, how do I write these electrons and show that this Lewis structure for sulfur has 6 electrons? Well, what I do is I imagine kind of 4 regions around an atom, right? Kind of as shown here in this box. 4 regions, and we can imagine those regions cut in half. And it's like there's 8 different spots where electrons can go, and we go filling those in similarly to how we filled in orbitals before, where everybody has to have 1 before we pair up, but then we can pair up. So without the boxes, it would just look like this. 1, 2, 3, 4, 5, 6, right? 6 valence electrons. So the Lewis structure of sulfur would look like that. Okay? So why don't we...
I have a question.
Yeah, go ahead.
You only drew 5 dots though. I maybe I missed something.
Oh, right. Sorry about that. 6. There we go. 1, 2, 3, 4, 5, 6. 6 valence electrons.
Okay, and does it matter where you put the next dot or no?
It doesn't. So
Okay.
that's a fair structure, but so is this, right? All right. Very good. So then, how about we identify some atoms here that we want to draw valence electrons for. Draw Lewis dot structures for. So here's one. Oops. Let me turn this on here. Okay, there's iodine. All right. Here's phosphorus. Here's nitrogen. Here's silicon. And here is selenium. Okay, so who were we just at? Precious. So Samantha, do you want to try to write the appropriate number of valence electrons, Samantha, around iodine? Taewon, do you want to do phosphorus? Harry, nitrogen? James Oliver, silicon? And James Wiley, Willis? Or Wiley? Willis, right, James?
Willis, yeah.
Around selenium. So, Harry, are you doing nitrogen?
Yes.
All right. James Oliver is doing silicon. See if you can learn how to turn the pen on there, James Oliver. It's in the top tools. You got to make sure it's drawing red or whatever color you want as well. There we go. We got it. Excellent. Okay, so iodine. Well, this was Samantha. Is that correct? Iodine. Samantha drew 7 valence electrons. Very good. Taewon put 5 around phosphorus. That's right. Harry's got 5 around nitrogen. Very good. James Willis got 6 around selenium. 1, 2, 3, 4, 5, 6. And James Oliver, how many do we got there, James? Is that 3 around silicon? I think we need 1 more, right? Don't we need 1 more? Yeah. So how did we know we needed 1 more? Well, silicon is in the 4th column when we're talking about representative elements. So let me go back to my screen here so we can see our periodic table, right? Wait. Silicon, there it is, silicon. So it's 1, 2, 3, 4. So again, silicon, 1, 2, 3, 4. Okay, very good. So now we can write Lewis structures for atoms, right? We're going to eventually work on writing Lewis structures for compounds. You can write Lewis structures for ions as well, but it's extremely boring because just to write a Lewis structure isn't very informative. The power of the Lewis structure comes when we can write the Lewis structure for a compound and learn information about that compound because of that Lewis structure, right? So here, for example, sodium with a positive charge sodium would generally have 1 valence electron, but with a positive charge, no valence electrons. So this would be a Lewis dot structure for sodium with a positive charge. Oxygen with a -2 charge, full valence, right? 8 electrons. Okay, so what do you think? How many electrons should be shown if we're going to have an N-3 ion? You guys want to write an answer down there at the bottom? How many electrons should be shown if it's an N-3 ion? All right, very good. 8 electrons. And that would be written like as follows. Nitrogen, 3 minus, 1, 2, 3, 4, 5, because it's nitrogen, and then 3 extra gives it 8 electrons. That's where we get our number 8. Okay, any questions about that? All right. So again, ionic compounds form bonds because once the electron moves from one element to the other, the resulting charges are brought together. All right. These bonds are relatively strong. And one of the reasons they're relatively strong is because if you look at the three-dimensional crystal lattice that results, you'll see that every atom, or ion, sorry, that is resulted has lots of neighbors. In fact, if I look at this sodium ion here, this silvery sodium ion that my mouse is pointing to, Catherine, how many neighbors would this sodium atom have if it were in the middle of the crystal? We've cut off the front part here, so take that into account. How many neighbors would this sodium atom have? Can you tell?
5.
It has 1 up here, 1 down here, 2, 3, 4, and then the 5th one is in the back. Is that right, Catherine?
Yeah.
That's right. So as it's written, it has 5. If it was in the middle of the crystal, it would have an additional one right in front here, wouldn't it? A 6th one. Okay. Katie Thomas, can you see how many neighbors, how many positively charged neighbors each of these chlorine ions has? So look at this one as an example. If this chlorine ion were right in the middle of a crystal structure, like this one here, how many neighboring sodium ions would it have? Are you there, Katie?
Would it have 5?
We have 1, 2, 3, 1 back behind that we can't see, 4, 1 in front that's gone so we can visualize it better, 6, and then it would have 1 down below. Sorry, start over. 1, 2, 3, 1 up above, 4, 1 in front, 5, and then 1 down below, 6. So just like this sodium ion has 6 neighboring chloride ions, each chloride ion also has 6 neighboring sodium ions around it. Can you guys see that? Can you visualize that? And that's where the strength of our lattice energy is, right? That's why so much energy is released when the ions come together to form three-dimensional lattices. So you can draw Lewis dot structures for ionic compounds, but that becomes really unhelpful because this doesn't tell us anything about the structure. However, when we draw Lewis dot structures for molecules, it can be helpful. So let's think about what's happening when we have a covalent bond. A covalent bond. Covalent is meaning same valency, the same valency. And if we think of something like sulfur and oxygen, right? They're both in the same boat in terms of valency. They both want 2 electrons to fill their shell. So if I have a compound that contains sulfur and oxygen, and a bond is formed between the sulfur and oxygen, that bond is forming because the electron density is being shared between the two. Sulfur and oxygen aren't in a situation where they can afford to give up electrons, like lithium, sodium, potassium, all these over here, right? If these are going to form compounds with each other, it's going to have to be a sharing experience. And this is what is occurring in that sharing experience. For example, 2 hydrogen atoms, right, with their 1s orbitals, which represent the electron density, the region where the electron density is, come close together, and the electron density begins to be attracted to the neighboring proton, and the result is a distance where the protons can stabilize because the electrons now have more region to interact with proton density, right? An electron here can interact some with this proton and some with that proton and form a bond. Okay? Now, if we think about the energy, the collective energy of 2 atoms of hydrogen, for example, it could be any 2 atoms though, but if we think about the collective energy of 2 atoms of hydrogen, all right, and we bring those 2 atoms of hydrogen closer together. Now, before we get any further, let's remember this concept here. If an atom is given an electron and this resulting ion forms, element given an electron, the change in energy for this process, will it be positive, negative, or it depends on the element? Whose turn is it? Landon, is it your turn? What do you think? The change in energy for this process, positive, negative, or it depends on the element? Do you remember?
Yeah, it's kind of like mine is tried. It's like receiving the child, so it'd be like positive.
Oh, it's negative.
Or it'd be negative.
Yeah,
Okay.
which means that it what? It's stabilizing the situation. Very good. So it's an example of a family receiving a child. Every family will be happy to take one child. It will stabilize the process. Now, everybody recognize that the answer was not, it depends on the element. The rule is that everybody will take one child and it will stabilize that family. Okay? Every element will take 1 electron and stabilize itself. Okay? What did we call that, Nikki? Do you remember? Is this, I'll give you a choice, is this ionization energy or electron affinity? Which one of those two is that?
It is electron affinity.
That's right, electron affinity. Very good. Electron affinity values are always negative. The energy values are always negative for the first electron. The second and the third, they're always positive, but the first electron is always negative. Okay, very good. So if we think about that in terms of two atoms coming close together, their energy starts here, but as they come close together, the electron density that they can begin to share stabilizes their collective energy until they get too close. If you get too close, then the positive charges begin to repel, or even the too much electron density can begin to repel each other. But when you reach this sweet spot, then your bond length is defined, right? It's defined as the length at which your energy is most stabilized compared to the collective energies of the atoms separate from each other. Okay? And this will be different for different atoms, right? If I have a hydrogen and a hydrogen, I'm going to get a specific bond length. If I have a hydrogen and a carbon, I'm going to get a little bit of a different shape and a different bond length, right? But again, along with that question, this is a question from nature that you need to make sure you recognize. If I have element A, this is an element, and I add element B, so these are both elements, and I create a compound, AB, does the delta H of this process positive, negative, or it depends? Positive, negative, or it depends? Precious. Element A and element B come together to form compound AB, delta H. Positive, negative, or it depends?
Is it negative?
It's negative. Very good. Always negative. If we're taking elements and forming a bond, then that means the process released energy. Okay? If it could not form a bond, if bringing those two elements in close proximity could not form a bond, then the bond would not form. But because a bond forms, that's an indication that energy was released. The same manner, we have, Samantha, this sort of a scenario, compound C and D broken up into its elements. Delta H for this reaction, positive, negative, or it depends, Samantha?
That would be positive because it requires energy.
It requires energy to do what? What did we do in this process? What did I break, Samantha? Did she write it down below there? What did I break, Samantha? How could I, what's that?
Broke bonds.
That's right. I broke a bond. I broke a bond between C and D, so it has to be positive. Anytime bonds are formed, it releases energy. Anytime bonds are broken, anytime bonds are broken, energy has to go into the system. Electron affinity, anytime an electron is given to an element, it will always release energy, at least the first electron. Okay, very good. So, molecules, when we're forming molecules again, molecular compounds bringing nonmetals together, we often follow this octet rule, and we can, as shown here, draw the Lewis structure for an element like hydrogen, the Lewis structure for an element like chlorine. 1, 2, 3, 4, 5, 6, 7 electrons around chlorine, right? We can look at the vacancies where electron density is lacking, and we can line them up so that we have chlorine 1, 2, 3, 4, 5, 6, 7, and hydrogen 1, right? And then draw them together so that I'll draw this as an X here to start off with, maybe that electron there as an X. So then I can differentiate it here, right? So here is chlorine, and then the hydrogen brings in its electron, and this is what we call a Lewis dot structure for this compound, HCl, hydrogen chloride, right? And a simpler way to draw that is to represent those electrons that are being shared between hydrogen and chlorine as HCl. All right? Represent the electron density that's being shared between hydrogen and chlorine as HCl. Sorry, as a bond.
Does it matter, like, if the H goes on the bottom or the top or the side?
It doesn't. So that is now equivalent to this, right? Or anywhere around there. We do want to kind of maintain our idea that there are 4 regions, right? And we speak of these electrons here. So what do you think, Taewan? How many electrons are represented by that bond there? How many electrons are represented by that bond? Any ideas, Taewan? This
2?
Yeah, that's right, 2. So anytime there's a bond, right? So for example, water, we've drawn this since day 1 about. Those 2 bonds represent, each one represents 2 electrons. So there's 4 electrons in all there. And we call those 4 electrons that are bonding, 4 electrons involved in bonding. And then we have 4 non-bonding. 4 non-bonding electrons. All right. So if we look back over here, Harry, how many non-bonding electrons do we have?
Maybe 6.
6 non-bonding electrons. How about bonding electrons, James Oliver? How many bonding electrons in a molecule of hydrogen chloride?
Could just be 2.
That's right. 2 non-bonding electrons. Okay, very good. So this is how we can use Lewis dot structures of elements to form Lewis dot structures of compounds. Okay. Now, I think that that's a good place to stop. So if there's any questions, I'd be happy to answer any questions. A little plug for lab. If you're in my lab section and you didn't get to go to, if you're in my Tuesday lab section and you didn't get to go to lab yesterday, the video is available to watch. Let me bring up this example of a Canvas page here. This is our general section, or our lecture section. Again, videos of lectures. Did I just show this at the beginning of the class? Yeah, I think I did, right? So let me sneak to my second section of lab, my Tuesday section. If you missed the Tuesday section of lab, this video shows you what we went over, or if you need a reminder or whatever. But we want to be on top of trying to finish up our lab section. So if you're in my lab section, make sure you take time to do that. Are there any other questions about anything? Not going to lie, those labs are hard. How many have you done, Nikki? Did you get to finish the second one yet?
I spent like 2 days trying to figure out the second one. Because, I mean, I did it with you on your thing, but then, like, I tried to go back. Well, I spent the whole first day trying to do it for myself, and then I just couldn't get it. And then I did the one with you in the class. And then after that, I tried to do it for myself, and I was getting so frustrated. So maybe I'll just go back and watch that video.
Okay. So we'll go over 2 of them. I mean, we went over 2 of them here in this video. And maybe we'll be able to go over 3 of them in the next class. So that would be 5. But I hope that as you get a better understanding of what's going to kind of being asked or whatever, not just you, Nikki, but everybody, that you can do better. But otherwise, if you have trouble, go ahead and email me. Let me know. This is the first time I've used these, so we have to figure out and answer questions as necessary. Okay, if there's any other questions, otherwise I will see you guys in lab or in class on Friday, right? Okay, have a nice day, you too.